Now, we can set up these cells, but they're not going to run forever. They only can release a certain amount of energy. And it's not just that they can only release and have transferred a certain number of electrons, but also the voltage changes as well. Because the spontaneity of these cells changes as the reaction proceeds. We know that the spontaneity of any process changes as the reaction proceeds. You see, we have discussed the standard cell value, the standard EMF for these cells, and that is when we have 1 molar concentrations of products and reactants. When we have 1 molar concentrations of products and reactants, our value of Q is 1. 1 over 1 is 1. Recall that Q is the concentration of products over reactants. But as the reaction proceeds, Q, you know, eventually must approach K until it's at a point of equilibrium. We know that Q will approach K to get to equilibrium, and we know that when we've reached equilibrium, the delta G is equal to 0 and the E cell is equal to 0 as well. As Q approaches K, E standard approaches 0. And so we can see then that we have this process where as we're going to the right, as we're having more and more products, the reaction is becoming less and less spontaneous until it eventually reaches equilibrium. And so what this means is that the voltage here is going down, down, down as the reaction progresses. Yes, the EMF of a cell depends on the Q, the product quotient, the concentration of products over reactants, reaction quotient, Q. It depends upon the concentrations of products and reactants, and eventually the voltage will decrease until it's equal to 0, and the battery is dead. You've seen dead batteries, and this is the reason that you get a dead battery. The voltage has fallen to the point of being 0. Now, we can do calculations with this concept. We've seen previously that delta G is equal to delta G standard plus RT ln of Q. But we also know that delta G is equal to negative NFE. And so we can replace delta G with that and replace delta G standard with negative NFE standard. And then we can take this new equation and divide both sides by negative NF so that we get E is equal to E standard minus RT over NF times the natural log of Q. And we know that R and T and Faraday's constant are all constant. Replace those with 0.0257 so that we get this final equation. The EMF of a cell is equal to the standard EMF of that cell minus 0.0257 over N times the natural log of Q. Or essentially we see that Q, the concentration of product versus reactant, affects the voltage of our cell, as we saw in the previous graph. So let's use this equation to determine will the following reaction occur spontaneously at 25 degrees Celsius if the concentration of the iron ion is 0.60 molar and the concentration of the cadmium ion is 0.010 molar. All right, so will this reaction occur? So we need to use this equation. This will tell us the value of E. If it's positive, the reaction will occur spontaneously. If it's 0, it's at equilibrium. If it's negative, then we know it actually will go in the reverse direction and be non-spontaneous. And so we need to calculate E standard and N as well as Q. Now, E standard, we know this is equal to the standard reduction potential of what is at the cathode, what is being reduced. And in this case, iron 2 is turning into iron. That is being reduced, so we'll plug in E standard of iron 2 as our standard reduction potential here for our cathode. And then for the anode, we'll plug in for cadmium. And then go to your standard reduction potentials chart, find these values. You find that the standard E cell is negative 0.04 volts. What that means is that if you had 1 molar concentration of both product and reactant, if you were at standard conditions, then this reaction would be non-spontaneous. Now we also can find N. Iron 2 is turning into iron. And there's only one of it, which is gaining 2 electrons, so 2 electrons are transferred during this process. N is equal to 2. And we also need Q. Now recall that Q is the concentrations of products over reactants at a given moment. Recall that you do include aqueous compounds such as cadmium and iron, but you do not include solids or pure liquids. So we only plug in the concentration of our cadmium ion product over the concentration of our iron ion reactant for our value for Q. And so we can plug in then to this equation and we get 0.013 volts. Or we have a positive value. Being positive, that means that this reaction is spontaneous. So this reaction will go ever so slightly for a little while until it also approaches equilibrium and its voltage is 0 as well, as all cells will do if they're being used. Now, another problem, kind of a little different though, is concentration cells. Those are cells that have the same elements in both half cells, but the half cells are of differing concentrations of that element, and so the cell can be driven spontaneously. It can have a positive voltage just by the difference in the concentrations of your compound. So, for example, if you were to have one half cell which had zinc solid and zinc ion at 0.10 molar concentration, and the other half cell was zinc ion at 1.0 molar concentration and zinc solid, what would be the voltage of this cell? What would be the EMF? And so, again, use this equation. Now, what is the standard E value? Well, this is kind of simple. You know it's equal to the standard reduction potential at the cathode minus the standard reduction potential at the anode. But in this case, you would be plugging in the standard reduction potential of zinc here and here. They would be the same value, so the overall EMF of the cell, standard EMF of the cell, is 0.00 volts. Now, what is the value of N? Zinc turns into zinc ion, and zinc ion turns into zinc. 2 electrons are transferred during this process. And then for Q, concentration of products over reactants, what is the product? Well, naturally, you should get to a point of equilibrium, where things are pretty much the same on both sides. Now, if you're starting with 1.0 molar on one end and 0.10 molar on the other end, it's going to have to be the case that you're going to lose some of that concentrated zinc and gain some of the dilute zinc. And so the product is that 0.10 molar, and the reactant is the 1.0 molar zinc ion. And so 0.10 over 1.0 is your value for Q. And now plug into the equation, you get E is equal to 0.0296 volts. Now, this is not a very large value. We've seen that having different elements would allow us to have very large E values, maybe around 1, sometimes 2. But this is a concentration cell, and it's really just driven by this difference in concentrations, and it only gives us a small EMF for the cell, which will again quickly decrease down to 0 as the system approaches equilibrium. The voltage eventually will fall to 0. Thanks for watching, guys.